Hi, my name is Tao Kai. I'm a senior studying material science and engineering with a minor in electrical engineering. And the Capstone project that I worked on was tuning electrical properties in gallium nitride nanowires for optimization of artificial photosynthesis. What really got me involved in this project was that I've always been really interested in renewable energy. And I really wanted to get outside of my comfort zone of working in a biology lab and kind of see if renewable energy is what I was really interested in. And I've always known about solar energy and like wind energy. I think these are very common, but it was really interesting to me to find out that there are other renewable energy sources out there that are equal in terms of how much potential they have in solving kind of the energy crisis we have. So to get started in the project, to give some background, obviously we know that it's very important for us right now to kind of get a renewable energy source that can replace fossil fuels, especially here as we see rising trends of CO2 in causing global temperatures to rise significantly over time, and that is a very pressing issue. And we know energy sources like solar and wind energy are very commonplace, but they kind of suffer in the department of it's really difficult to transfer this energy over long distances. Electricity will dissipate over time with resistance in wires, and it's really hard to move energy from like one state to another. But something that's really pretty easy to move is hydrogen. Hydrogen gas is really energy dense and really easy to move around. And people have talked about using it as an energy source for a long time, especially in cars. But it's pretty difficult to produce hydrogen gas. And so some really smart people, they come up with this process that they termed artificial photosynthesis. And the Me lab here at the University of Michigan, they've really tackled this problem and kind of pushed it to its limits. So what exactly is artificial photosynthesis? It's photosynthesis in the sense that it uses sunlight, but what we're really doing is that we're harnessing the sun and kind of utilizing and taking advantage of the sun to speed up the process of water splitting to generate hydrogen gas. And that hydrogen gas can be used to generate electricity, can be used to power our cars, can be used to power our homes. It can be used for a variety of sources. So what exactly is water splitting? It's this chemical reaction that you see here. Overall, it's taking water and splitting it into hydrogen gas and oxygen gas. The oxygen gas is what we breathe in. It's a harmless byproduct, and in fact, it's a helpful byproduct. And hydrogen gas is the fuel source that's very efficient for us to use. And the Me lab, what they figured out in terms of this artificial photosynthesis process, how they can make it more efficient, is that they've added two components inside of their device. The first is a semiconducting nanowire. Semiconductors have this trait in them that electrons are relatively mobile, and electrons are what is used to generate electricity. And so electrons being somewhat mobile means that we have a quantity of electrons that are mobilized and a quantity that aren't. And if you give enough energy to these immobile electrons, you can make them mobile. And what we're using these nanowires for is that we're taking sunlight to provide the energy to those less mobile electrons and mobilize them so that they can be used for, in many cases, semiconductors are used for electricity, but for us, we're just taking those electrons from those immobile electrons and using them inside of this water splitting reaction. So you can see here that in this half reaction on the top, that electrons are a reactant. And if you remember from chemistry, if you increase the concentration of reactants, you can increase the concentration of products. So as we provide more electrons from this nanowire to our reaction, we end up producing more hydrogen gas that speeds up the rate that we are doing this water splitting process. And similarly, we have a photocatalyst. So a regular catalyst is a material that speeds up reactions by making them more energetically favorable in a sense. We provide sites where the reaction is more easily able to occur. And photocatalysts are catalysts that either only work or work more efficiently in the presence of sunlight. And so you can see how both of these processes harness the power, the energy coming from the sun, and make this process of water splitting more feasible or more fast. And so this is an outline of what makes our device work. And here on the right, they've tested this. They've combined a superconducting nanowires and they've added photocatalysts into a device. And they're shining LED onto this device, and that's filled with water, and you can see that there are these bubbles, which are the hydrogen gas and oxygen gas coming out of the water. So they've demonstrated that they've been able to successfully split water very quickly, very efficiently with this device, but it's not quite yet ready for commercialization. So what my project was to kind of look more into what parameters affect these kind of performance metrics of our device, and how can we actually increase the efficiency so that we have something that can actually be used in a more commercial setting. And so what we looked at was we performed density functional theory to kind of observe how gallium nitride, these electrons, actually move around, and the distribution of electrons inside of this material, to kind of look at whether or not this semiconducting nanowire electron transfer process is both actually what's responsible for accelerating our reaction, and whether or not it's actually efficiently moving electrons to our reaction. So what density functional theory is it's this theory that has been proven is very accurate in predicting electron distributions, which is extremely complex. And they've been able to do this by simplifying the problem significantly. And so this makes it possible for computers to actually compute and run this density functional theory and actually predict electron structures, which would normally take like the most powerful computers you can ever imagine. And so what I did was that I performed some density functional theory and focused on seeing how temperature affects the electron distribution, because temperature is both something that electrons kind of vary a lot with. Electrons are very sensitive to temperature in terms of temperature affects the electrons themselves, but also affects the surrounding lattice of the material, which makes it difficult for electrons to move properly. And also temperature is something that we can more easily control in our device. Temperature, we can adjust the concentrator of our system to change the temperature and how much we're actually heating the water and subsequently the material itself. So in theory, we kind of predict that there is kind of this balance of temperature in terms of we want high enough temperatures to provide energy to our electrons so they can actually be excited. But also too much energy and too much heat causes causes atoms in our material to vibrate a lot. And you can imagine if you have an atom moving a lot and you're trying to send an electron through, it's more likely for the electron to collide with the material if this atom is moving all around rather than if it's in one place and the electron can easily slide by. And so what I did was I ran simulations on gallium nitride using a software called Material Studio. What this software does is it actually runs this density functional theory under different conditions that you specify. And these are the parameters that I used. I came up with using these parameters based on considering how our system actually functions and what kind of energetics we want to consider inside of our system. And some of the results are shown below here, that we have different temperatures where we are running this density functional theory, and we have different electron distributions. So to read these graphs, the x-axis is the energy. So you can think of, the x-axis is energy and the y-axis is the density of states, which describes where electrons can occupy and are being occupied. And so you can think of these on the left side of the graph, there are electrons here that are very low in energy, and on the very right, these electrons have higher energy. And so you see there are no electrons up to a point. The reason there are no electrons here is because there's something called a band gap in semiconductors where electrons don't exist. And over here, we have an increasing amount of electrons with energy. And this is because we're exciting more and more electrons when more and more photons kind of hit our system. And we see that as we increase temperature, we have an increase in the number of electrons that are present in our system, which is what we expect. And that's only up to a point. Eventually, as we reach higher and higher temperatures, the electron density actually decreases. And that is shown in this figure over here. It shows the density of state with temperature at 8 electron volts. And very interestingly, this matches kind of the general trend that we expected for our theory, but it doesn't exactly match the exact numbers that we had predicted. So to talk more about that, we performed density functional theory at these different temperatures. And we saw that there's this huge initial jump in terms of the density of states from 0 to 20 degrees Celsius, but it kind of plateaus after that. We kind of expect there to be I definitely expect there to be a significant increase as we are exciting more and more electrons. And we kind of think that the reason that this gradient kind of decreases over time is because we have stronger influence from scattering as we increase the temperature, but we don't expect it to be this significant in that we have such a huge jump and suddenly this increases leveled out significantly. And so it's interesting that we are able to somewhat match the trend, but in terms of the actual specifics of matching this up to theory, we won't be able to correlate this data directly to some of our predictions. And so in terms of whether or not this is successful, that's really hard to say. And for future, we really want to improve the accuracy of the simulation. And we want to perform more DFT, possibly with different ensembles, different specifications of our process and environment. And the overall goal of this project is to compare these simulations to actual operating conditions with our successful device. We want to run the device with different temperatures and compare those results to theory to see whether or not we can observe some sort of scientific phenomena, whether we can observe something new that is causing our results to vary significantly from simulation. And if they do match very closely, then we can figure out from simulation how we can optimize these operating conditions for our device for possibly commercialization in the future. And so these pictures on the right are a solar concentrator and a setup of the device that we actually have here at the University of Michigan, where they are actually testing this device and able to successfully split water by concentrating sunlight. And so that's this project. Thank you so much, first and foremost, to my mentor, Peng Zhou, and the advisor, Professor Mi, and everybody else in the Engineering Honors Office. Definitely, in terms of what I hope to accomplish, I don't think I accomplished as much in this project as I wanted to. It was quite difficult to balance everything in senior year, but I'm definitely hoping that if I can continue working on this in the summer, that I can possibly find some interesting results and actually do some comparison with actual physical experiments, because that would be really interesting. So thank you guys for your time and have a great day.